Hello everyone. In this video we are going to look at the fundamental equations of elasticity, and I said before I go to different cases like axial loading, bending, torsion, combined loading, shear, and so on. Let me just look at the big picture first and the big equations that we have, and then we can go into individual cases. So here we are looking at an infinitesimal element. It has dimensions dx, dy, and dz. Okay, so it's a very, very small element inside the material. And this element has, of course, it's a cube. So as you can see, it has 6 faces. On each one of these faces, there are 3 stress components. Normal to that face, you have the normal, of course, stress. And then tangent to that face, there are 2 components, each one in a different direction. So for instance, if you look at this top face here, you can see that the vector normal to this face is y-axis. So any stress component on this face, the first component of it is a y. So it's sigma yy, or just sigma y, and then the taus, if you look at them, this is tau yz, and this one is yx. So the first component in a stress, as I said, is a tensor rank 2. It needs 2 direction. The first component shows the normal vector to the face. The second one is the one showing the direction. So if it's a sigma, then the second component has to be the same as the first component because it's normal. But if it's a shear, the second one shows the direction. So you see, this is tau yx, means normal to the y in the x-axis direction. And if you look at this axis, that is the same as the x-axis. And this one here, this guy is in the z-axis, so it is tau yz. Okay, so clearly you see how to read these stress components. So as I said, on each face we have one of these, and these stresses are functions of location. They are not constant within the material. So any of these 6 components of the stress, and remember these shear ones are the same. Probably I show it in a separate video for you. So there are 2 things that I can show you in a separate video. One is why these shear components are equal. Yx and xy, y is your tensor, is a symmetric tensor. The other one was that formula we had, G equals E over 2 times 1 plus nu. Okay, I'm going to show this, and y tau xy equals tau yx. I will show these in a separate video. Okay, I don't want to do any proof in this video. So for now, if you assume that they are the same, then all of these stress components, these 6 of them, sigma x, sigma y, sigma z, and the 3 taus, all of these are functions of location. Okay, all of them are clearly functions of location. And so if on this bottom left corner here in this back, the stresses are sigma x, sigma y, sigma z, and so on, when you move in the x, y, z direction, they change, right? So if we look in this z direction, what do we see? If you look in this z direction, we see this square. And then remember, the faces are perpendicular to the x-axis. So if this guy is sigma x, when you move a distance dx, this one is not going to be sigma x as well. This is going to be sigma xx plus some extra term. Now, what extra term? That extra term comes from the basically the small expansion, the first term in a Taylor series. So that is going to be the partial of sigma xx with respect to x, because you only moved in the x direction, times dx, or delta x in this case. Okay, so this is the first term of a Taylor series expansion. Why don't you add the higher order terms? Because these dx's are very, very small. When you raise them to the power 2, 3, 4, they are going to be much, much smaller than the rest, and you can ignore them in terms of order of magnitude. So for that reason, we only consider the first term. And similarly here, if you look at this guy, this is perpendicular to the y. So if this one is called sigma y, clearly this one is sigma y plus this increase because you moved in the y direction. So it is going to be partial of sigma y, or yy, you might want to call it, with respect to the y times dy or delta y. And the same goes for the taus, right? So if at this bottom surface here, this guy is tau yx, then on this top one here, this is going to be tau yx, or xy, doesn't make any difference, plus what? Well, in this top surface, clearly you moved in the y direction, so it's going to be partial of tau xy, or yx, with respect to y times dy. You see? And very similar thing for these two other faces. So here, if this one is tau xy, then this is going to be tau xy, or yx, again, doesn't make any difference, plus partial of it with respect to, you moved in the x direction, and times dx. Okay, so this is like a 2D version of that, and we can look at it in 3D as well. So as you can see, each component has some increase when you move along x, y, or z. So this is my infinitesimal elements, and there are other forces as well. We call them body forces. So these guys are called body forces. They are the forces that are applied to the volume, not to the face. Body or volume forces. Like what? Like mg. So if you have gravity, the gravity is something times this volume, which is dx, dy, dz. Okay, and it could be in any direction. In this case, maybe, for instance, if it's downward, there is only a y component, x and z are 0, or they could be forces due to electromagnetic or any other thing. Okay, so these are body forces, not forces on the faces. So now, with all of these forces that you can have, we want to write the equations of equilibrium for this infinitesimal element, which leads to these three equations, which we call them equilibrium equations in elasticity, and we're going to derive them, at least one of them. I derived one of them for you. The other ones, you can see that they're going to be basically obtained using similar logic, and then basically we are going to move on to the rest of the equations. So here, if I write the equilibrium in the x direction, that sum fx equals 0, correct? This is a static scenario. Now, what forces do we have in the x direction? Let's look at all the forces that we have on this FBD of this infinitesimal element. Let's look at all of them that are in the x direction. Which forces are in the x direction? Well, clearly this force is in the x direction. This force is in the x direction, right? Let's find anything. This guy is in the x direction. This one is in the x direction. And so these are x, y, and yx, sigma, sigma. And then on these front faces, if you look, this force, look at that. That force is in the x direction. And on the back, it's this guy here. So there are 6 forces that are acting in the positive or negative x direction. And we have to add and subtract them to get what we want, plus, of course, this fx force. So let's write it. What is the force that we have due to sigma x? And here, each element has some area, so the force is that stress times that area. So this force is in the negative x direction, so negative sigma xx. And what's the area of that face? Well, that face has a d x direction followed by a dz direction, correct? So these are the dimensions of that, or dy, I'm sorry, dy, not dz, this guy. So it is going to be that times dy dz, or delta y delta z. That is the force for that guy. Now this one, which is the opposite side of that, is going to be positive. and the area it is applied to is similar, dy dz. So far, that's the total of these two forces. The other force you have is this tau yx, and it's negative, so negative tau yx. Where is it? It's on this bottom face here. It is applied to the bottom face. Why? How do I know? Because first of all, it's a dash line, so it means it should be behind something. Second of all, the first component of it is y, so the y should be perpendicular to it. And the only two faces that have y normal to them are at the top and the bottom surface. So this is the bottom surface. And the area of the bottom surface is clearly what? It's dx, right, in this direction, and dz in this direction. So this is going to go d x times dz. The counterpart of that is this force here on this top, which is plus, you see it's in this direction, tau yx plus partial of tau yx with respect to y dy times the area of the top surface, which is the same as the bottom surface, and that is dx dz. So we got these four forces now. Finally, let's go to the last two forces. So I got this one, I got this one, I got this one, and I got that. So the last forces we have is this tau zx, which is on the back surface, and it's negative, so negative tau zx. The area for the back surface is a dx times dy. And the counterpart of that is this guy here in the front face. So plus tau zx plus partial of tau zx with respect to x dx. Okay. Or with respect to z dz, I'm sorry, times the area of the front, which is also dx dy. So here we added all of these six forces on the faces, and now we have to add the body force. What is the body force? As we said, these are the forces per volume. These are all of them are the type of force per volume. Okay, these are forces these are densities. So the force, because of fx, is going to be positive fx times volume of this cube, which is clearly dx dy dz, and this whole thing is equal to 0. Now if you look here, this first term here is sigma xx dy dz. This is negative sigma xx dy dz, so those two terms would cancel. Similarly, in the second one, this one and this first one multiplied by the dx dz cancel, and in the last one, these two would cancel. Okay, so these single terms would cancel, only the ones that have partials will stay. And now, if you look at the partial terms, look what they all share. They all share dx dy dz. And this guy also has dx dy dz. So guess what? We can get rid of all of these dx dy dz's. So if we simplify, there is only this partial left, this partial left, this partial left, and fx. And that is exactly this first equation. There we go. So we got the first equation. Similarly, write some fy and some fz equals 0, and you get the second and the third equation. So these equations are the equilibrium equations, which show that how the stresses on the faces or based on location should change such that the element, any element, has equilibrium and does not move. Okay, so these are sigmas related to the body forces, and clearly you can see that these are differential equations, correct? Partial differential equations, because in general these components of the stress, all of the 6 components, can be functions of x, y, and z. So these are 3 partial differential equations that you are getting here. Okay, now moving on with the Hooke's law. So we know Hooke's law. We saw it in one of my previous videos on the basics or fundamentals of elasticity. So Hooke's law is, if you remember, the one we had was the stress sigma x was what, or sigma in general was E times epsilon, correct? In any direction, the normal stress in the linear region, so this Hooke's law is only good in the linear region. If the material showing any linearity, this kind of behavior is observed in the linear region, and for any direction you can write it. So in the x direction you can write x, in the y direction you can write y, in the z direction you can write z. Good. Also, we learned that the lateral deflections or lateral strains are related to the axial ones. So we learned that, for instance, epsilon y equals nu times epsilon x if the load is in the x direction. The same thing with the z. We also learned this, right? So these two are lateral deflection. X is the axial one, and this nu was the Poisson's ratio. So we learned this one and this one. Now, these were for 1D loading case. In 3D, when you have all three components of X, Y, Z, whether strain or stress, available, then you have to extend these two laws to the 3D. So how do you do that? Well, you say, well, epsilon x is how much? Epsilon x is clearly sigma x, or if we call it xx, is sigma xx over E, correct? That is the strain you get in the x direction because of the normal stress in the x direction. But also, if there is a epsilon y or epsilon z as well in the material because of the loading in those directions, then I can say there is epsilon xx, which is negative nu times epsilon yy, and there is another epsilon xx, which is negative nu times epsilon zz, right? So if I do axial loading in the z, there is some lateral in the x. If I do axial in the y, there is lateral again in the x. So my total epsilon x should be sum of these three terms together, right? Because there is axial loading here in all three directions. I have to add these three terms together to get my total epsilon xx. Now the thing is, what is epsilon yy itself? This guy, how much is it? Well, similarly, this you can write it as sigma yy over E, and this one you can write it as sigma zz over E. So if you do that and you factor out all these e's that are in the denominator, you are going to get this formula here. Look at it. The e is there. The first one has no coefficient of sigma xx is 1. The second one has a negative nu. The third one has a negative nu, as you can see. So this is epsilon xx based on the sigmas in the y direction, z and x. This is epsilon yy, similarly based on, again, the stresses in the other direction. And this is epsilon zz based on those directions. So here we are relating the stresses to the strains, to the normal strains. Normal stresses to the normal strains. What about the shear ones? When we learned that in the shear stress, we learned that tau in the linear region, again, is equal to a constant g, the shear modulus, times gamma. Now, this can be written for any direction. So if this is xy, then this is xy. If this is xz, then this is xz. And if this is yz, then this is yz. And those are these equations that you will get. So these 6 equations are going to give you relations between stresses and strains, assuming your material is acting in the linear region. So these are Hooke's law, which are only for material that's showing any linearity. So they are not really applying to hyperelastic material. And the other important thing that you have to mention is the material is isotropic. What does that mean? Means if you move in this material from this point in any direction, x, y, z, doesn't matter which direction you move, and go from this point to this point to this point, the E, the Young modulus that you have in this direction, x, is the same as the Young modulus that you have in this direction, y, is the same as z. So the material is homogeneous, and it is also isotropic here, which means there is only one Young modulus in any direction, there is only one Poisson's ratio, and there is only one shear modulus. There are not three. There are material that can have different E's. So they have EX and EY different than EX, or new X and new Y. Like what material? Like composites. In composite material, clearly the E's in each direction, they are not all the same. Or if you 3D print a plastic, if you print a plastic layer by layer, the material is always weaker in this direction of the print than in this direction. So if you call this, for instance, EY and this is EX, clearly EY is less than EX. Okay? If you can assign an E to them, clearly the material is weaker in one direction than the other directions. Okay? So a 3D printed material, whether it's from any kind of plastic, doesn't matter, PLA, ABS, it is never isotropic. And again, composites. Composites are designed such that they are strong in the direction that is carrying load and not as strong in the directions that they don't carry load. Okay, so here these equations are assuming that everything is isotropic. Okay, there is one E, one G, and one nu. So these are the second set of equations relating stresses to strain. The first ones, we related the stresses to forces. These were partial differential equations. These guys are not partial differential equations. These are algebraic equations. As you can see, there is no derivative anywhere. So if I have the stresses by some multiplication and division and adding subtraction, I can easily get the strains. Okay, so these are algebraic equations. Now, the last set of equations that we have to look at are the relations between strains and we call them displacements or field displacements. And these are going to be, again, differential equations as well. So let's look at those. So you know that when you apply load on some material, different points on the material will move, correct? The whole object will not move. It's in static scenario, but it has deflections, it has deformations, different points, right? So when you have this beam and it's like a simply supported beam, when I apply this load, the whole beam will not move in the X or Y direction and it's not going to rotate. But if you look at the beam after deflection, you're going to see something like this. So if you looked at the point that was here, now it might be here, right? So different points move and in different amounts, and depending on their location, they move differently. So if at any arbitrary point, like this point here on this cube, I can say that this point here can move in three different directions, X, Y, and Z, and the displacement in those directions, I would give them some name. So in the X direction, for instance, if you look at this, this is X direction. So in the X direction, I call the displacement at that point U. In the Y direction, I call it V. And in the depth direction, I call it W. Okay, these are how much that point moves in any of the three major directions. Then clearly these displacements or displacement fields, you might call them, they are functions of the location. I mean, this U at this corner and U at this corner, they are not the same. If they are, then this element AB will never be stretched or compressed, right? And there will be no angular deformation or axial deformation. So there will be no strain. If everything moves the same amount, then your whole part will move and it's going to be displacement. It's not going to be deformation. So here we need to have these values change over some distance. So we say that U, V, and W are functions of locations X, Y, and Z. And the question is, what kind of function satisfies your elasticity and linearity? So here, again, we look at that same infinitesimal element that we had up there, but here it's shown with deformations. So I say, if I look at A and B, okay, and let's look at it for 1 second in the Z direction only, because this 3D might be a little bit intimidating. So if I look at it, or if just look at it in 1D, just look at the line AB. So this is line AB. Just let's focus on this one, so it's less intimidating. So how can I relate the strains to the displacement? Remember, this point here moves by u, so u. The length of the element is dx. Now, how much this other point move? Well, similar to the stresses, remember how we added this first term Taylor expansion to show how much the stress has moved. We do a very similar thing for the u's and v's. So if this point is u, this point will move as u plus partial of u with respect to x dx. We add the first term of Taylor expansion. This is how much this point moves. Similarly, if this point in the y direction moves by v, this point here is going to move by v plus what? Well, the only difference between these two is dx, so it's going to be partial of v with respect to x dx. Yes? Now, what happens if that's the case? So this point moved so much, u and v. This point moves a little bit more, both in u and v. So if this point comes from here to here, this point goes from here to here for x. And if this point goes y like this point, it's going to go a little bit up like that. And so, of course, it comes here because it moves both in the x and y direction. So you go from this point to that point. So you're going to get this element. So now if you look at the green version and the red version, if I call them A and B again, or A prime, B prime, you see that not only the length of the element has changed, also the angle of the element has changed too. And if it was horizontal, it's not horizontal anymore because one side went up more than the other side did. So the question is, how do I measure these entities? The first thing is the change in the length, epsilon x, the strain, axial strain. What's the definition of this? If you remember, the definition is delta L over L. But in which direction? In the x direction. So this is delta L in the x direction over initial length in the x direction. And how much is the initial length? The initial length is dx. And how much is the change in the length? Well, the change in the length is the displacement axially in the right side minus the displacement in the left side. So it is u plus partial of u with respect to x dx minus u. Correct? The displacement axially on the right minus the left. And clearly, this 2u would cancel, and then dx would cancel. And guess what you would get? Just partial of u with respect to x. So partial of u with respect to x is going to be epsilon xx. So you see that epsilon xx is the first partial derivative of u with respect to x, and this is exactly this formula. So you see I can relate the displacement in the x direction, their derivatives, with the strain in the x direction. Similarly, for y and z, I can show these formulas. Okay, if I look in the other directions, if I look in the y or z directions, I can easily show that. Now, what about the gamma? What about the change in the angle? So where does the change in the angle come from? Well, if I go back and look at this, let me do a little bit cleaning if you don't mind, or actually let me put this back. I just need to do some cleaning, maybe just this part. So what is the angle that you created? The angle that you created is this angle here, whatever it is. Let's find it. And that's not it. There is a counterpart on the other side too. So it's actually this angle plus this angle. The total of that is your gamma. So if I want gamma xy is actually angle alpha plus angle beta, because that's the total change in the 90-degree angle. Your 90 degrees is now 90 minus alpha minus beta. So the total gamma, the change in the 90-degree angle for the xy, is alpha plus beta. The question is, how much is alpha, how much is beta? Well, this angle is beta based on that picture. So how much is beta in this case? Well, if you look at this triangle that you have, where this is point A, the new A prime you might call it, and this is the B prime. So what is this difference in the y displacement between A and B? Well, this point moved by V, the other point moved by V plus this partial. So this length here that B moved further up is partial of V with respect to x dx. That is how much B moved further up compared to A. Agreed? Now, what is this length? This length is dx, approximately, and this angle is beta. Well, how much is beta? Well, beta, or tangent of beta in this case, is equal to the vertical side over the horizontal side. So if you divide this by this, the dx's would cancel. You get partial of v with respect to x. But remember, these are all infinitesimal elements, and beta is also a small angle, so I can say beta is the same as tangent of beta. Especially when x dx goes to 0, they are equal. So beta is partial of v with respect to x, that is that angle in radians. Now alpha, if you look at it, is similarly this side moved by u, this other side moved by u plus partial of u with respect to y dy. So the difference between them is only this much, and that divided by this vertical side from here to here, which is dy. If you divide that by this, that is going to be angle alpha. So alpha is what? Partial of u with respect to x. So if you add partial of u with respect to x to the partial of v with respect to y, that should give you gamma, and that is exactly this formula. That is the change in the angle xy, and similarly, you can show the changes in the angles xz and yz. So these 6 partial differential equations are going to take you from the displacements to what? To the strains. Okay? So now you see I have a set of equations. I have u, v, and w, the displacements. If I take partial of them, I get my strain tensor. So I get this. So I use these equations, these 6 equations that I showed you. From these strains, I can go to the stress tensor. Right? So you go by the Hooke's law, and finally from here you can go to the body forces. Through the equilibrium equations. And many times you have backwards. Many times you have the body forces plus external forces. So you have to solve those equations to go there, and then you go through Hooke's to the strains, and from the strains you can go to the displacements. Okay, in finite element analysis, you start from here and you end up there. Okay, but you see how I can go between them through these equations that you just saw. Now here we are going to look at a simple example, and there are some steps that we just get it from the results of beam deflection. So we are not doing all of it, but the example is a cantilevered beam with length L fixed at x of 0, free at x of L. There is the negative load Q downward with uniform intensity, and we want to look at the deflections. u, v, and w in this case at different points as a function, because remember, we want to find these guys basically. Now, in this case, everything is happening in the xy direction, so the z components we can simply neglect. So we can simply neglect any z. So the w altogether, along with epsilon zz, along with gamma xz and gamma yz and sigma zz and tau xz and tau yz, we can neglect all of them because nothing is happening in the z direction, no changes. Now, epsilon zz is not necessarily zero in this case, okay? It's not really zero. Okay, we'll talk about that later, but it's not necessarily zero, but the other ones we can talk about them. Because this is a plane strain, and epsilon zz is not necessarily zero because, you know, it can come from the Hooke's law. If you look at the Hooke's law here, even if there is no sigma zz, because of sigma xx and yy, you still can have epsilon zz. And in this case, even if you neglect sigma yy, there is still epsilon zz because of epsilon x, because of sigma xx, which is non-zero. So epsilon zz in this case is not really zero, but the other ones we can neglect. And now if we go and look at it, the first thing we need to do is, of course, we need to find the free body diagram so we can find the support reactions at this cantilever. The axial load is zero, the vertical load and the bending moment we can easily find by replacing the uniform load by a single load, which is QL, and exactly in the middle we can find the shear force to be QL and the bending moment to be QL squared over 2. So these are the support reactions. Now what we need to do is to go ahead and cut it at location X. So now we move in this direction by amount X, we cut it, and we look at the free body diagram of that portion. So we have to again replace Q over distance X by QX in the middle. And we have these reactions here on the left, and on the right side, we have M of X and we have V of X. The shear force and the bending moment as a function of location. Again, using the equilibrium, we can find these two functions. So M is a quadratic function of location and V is a linear function of location. Okay, so these are very easy. You can easily do that by statics. It's no big deal. And you can see that here, right? So negative V, negative QX is positive QL. So if you subtract, factor out Q, you easily see how you get V, and take some of the moments about this point. And the only moments you will have is this guy and this one, and of course this one as well, that one, this one, and this one. Okay, and you can find that. Or if you take it about this point, then you will have this QL, you have the QL over 2 and the QX, and there are 3 terms which you can factor it as this quadratic equation. So this is V and this is M. Now, this is the part that we are kind of cheating and using the beam theory. So we say in beam theory, we assume that first of all, sigma yy is small, no normal stress in this direction. The only stress happening is in the x direction. How much is in the x direction? We'll see later when we go to the beam deflection and the beam bending. We'll see that the sigma xx at x location or y location is negative mx times y over izz. And what is that? Well, if you look at this beam here, the beam, if you go back, let me go up a little bit, the beam is like this. So this is how the beam is. This direction is x, this direction is y, and this direction is z. And the dimensions are b and h. So b is the width and h is the height for, in this case, this rectangular cross section. And this is passing through the center of that rectangle, of course. So the stress at any cross section depends, of course, on where you cut it, and also depends on where on this cross section. Is it at the top of the beam, or it's at the bottom of the beam, or in the center? It depends on your height on the beam cross section, and it depends on I of the beam about this horizontal axis ZZ. So it is this formula, which we're going to see, negative my over z, and m is a function of x. If I plug this function in it, this is going to be sigma in the x direction as a function of both x and y. And again, you'll see, and remember sigma yy, we said this guy is 0. Tau xy, the shear, again, we'll see later, it is equal to the shear force V times qy over izzb. Izz is the same as before. B is the width of the beam. Qy is what we call the first moment at the location y and above. So if you look at this cross section, and again, we're going to see that. So if you look at this cross section here, and you go to the location y, the area of this cross section above the y location, this one, the first moment of that area with respect to this neutral, what we call neutral axis, the first moment of that area with respect to this neutral axis, which is integral of y dA over which a? This a. When we say a, means that small portion. That is that qy that you can see, and clearly it depends on y. Okay, so clearly it depends on y, so that is this qy. So if I find that qy, which is basically this one here, and vx, and plug it in, this is going to be the shear stress based on x and y. And izz is clearly based on what we know from moments of surface. Second moments is bh cubed over 12. So now that we have everything, we have sigma xx, we have tau xy, and sigma yy is 0. So it's a 2D case. We have the elements of the stress tensor in the 2D case. Now that I have sigmas, it is time to look into epsilons. So I have the stresses. Now I have to look at the strain. So here I already had this to begin with. I did not even go to the body forces or anything. And by the way, when we derive those formulas, these are all neglected. We'll see. We don't bring in the weight of the beam. And we neglect those. We just look at the Q force. And so far we have this portion that we care about. And so now that we have it, it's time to look at the strains. And then from strains, we can go to the field displacement. Now going from here to here, remember that is the Hooke's law. So here we are going to apply the Hooke's laws that we learned, right? These equations here. And the only ones we want are these three. So this one, and this one. In this case, of course, again, there is an epsilon zz in this case as well. So we can find them, and you can see that here. This is epsilon xx, this is epsilon yy, this is gamma xy. And this guy here that you can see, you might say, what is that? That is 1 over g. Remember, g was e over 2 times 1 plus nu. So when we say, and this sigma xy is actually the same as tau xy here. Okay, so this is 1 over g, that guy that you see here. So these are the functions that you find for a strain as a function of x and y. Good. Now we want to find the axial displacement u and v. In this case, they are only a function of x and y. There is no z, and remember w, we said we neglect it. So the only things we have in this case are x and y. There is no w and there is no z here. Everything along z is constant, so they are only functions of x and y, and that is what we need to find. So we go ahead and use our relations, epsilon xx that we just found earlier, this one. This is the partial of u with respect to x. Remember the formulas that we derived, so we are going to use this first one first. And we try to find the u function by integrating. So here we are integrating with respect to x. So we integrate basically this function with respect to x. It's a cubic function of x, a quadratic function of x, so you get a cubic function of x. And since you're integrating with respect to x, you can have a constant term but it doesn't need to be really constant like 2, 3. It could be a function of y in general. So your constant could be a function of y, and this function of y could have that constant number c1, which is 2, 3, the integrate constant in it. So remember, when you solve partial differential equations, if you integrate with respect to y, the constant is going to be a function of y when you integrate with respect to x. If you integrate with respect to y, the constant term is going to be a function of x. Because if you go back and take partial with respect to x from here, you're going to get this guy back. Okay, this has no derivative with respect to x. So that is your u function. And the question is now, what is that fy function? We have to find that constant of the integration. The question is, what is this? For that, you need to apply a boundary condition. What is the boundary condition? At point 0, 0, at the root of the beam on the left side, there is no displacement. This point is fixed. It cannot move u, it cannot move v. In this point, u and v are both 0. At this point, x0 and y0. There is no displacement, so you have boundary condition here. So you plug that in, so you plug x of 0, y of 0, and clearly that means fy has to be 0 as well. So this is your u function. You found your vector field u. Now what? Now you go to the gamma xy. Gamma xy is this function. So now we are going to go up here and use this formula. And the first term, partial of u with respect to y, well, we just find it. We take a partial of that with respect to y. We get this. We plug it into this, and we find partial of v with respect to x. Okay, so we have gamma xy, which we just found earlier. This one, this function. We subtract it from this partial of v with respect to y. And then once we have partial of v with respect to x, we are going to integrate both sides with respect to x. So we can get v function. And v function is going to be this, integral of it with respect to x, which is going to be this one. Again, when you integrate with respect to x, you're going to get another function of y as a constant of integration. But again, remember that v at 0 and 0 is also 0. That means this g of y is also 0. So this is going to be your v function. And that top is your u function. Done. So I found my vector fields as well here. And again, remember, there is no w and there is no dependence on z. So here I try to go through the 3D fundamental equations of elasticity. And not just elasticity. Remember, there are two other constraints. One, the material should act in the linear region, and the material should be isotropic. So these equations are valid. Otherwise, some or all of them will not be valid. Okay, this top one is going to be valid regardless, but these bottom ones, not always. So hopefully this video was useful to you, and I'm going to see you in the next lecture. Thank you.